record in the cloud. I have started recording in the cloud. Now I'm going to discuss about derivations of the Poisson regression model. So derivation of Poisson regression model. Remember, in the last class, I wrote a equation, right? And say that this is the simple linear equations. And then I also wrote these equations, x beta plus epsilon, say that this is the multiple linear regressions. This is simple linear regression. Clear, right? This is how did I explain these things? I explained these things by writing a linear equations, and which was written 2300 years ago, more than 2500 years ago, like by Euclid and other people as the equation of a straight line. Geometry was developed 300 BC by the Euclid. And 1805, Galton just added an arrow term of that straight line equations and call it as a regression model. Okay, so now how can I come into this point? And most importantly, when I say derivation of the Poisson regression model, so that means how can I estimate these betas? That is the unknown, that is the parameter. I have to estimate these betas by using y and x so that I can make a predictions. For a new set of given x, I want to predict the y. Understand, regression is the only tool that can predict, right? From a given set of data, I can estimate the parameter, and then I said that, well, my unknown parameter constants are estimated. Now I want to predict future values based on some given values for the x's. That is the fundamentals of the predictive modeling. Okay, now take a look at that. I said lambda is the mean of Poisson distributions, right? That I mathematically derived. Can I write like this way? Log of lambda could be written as beta 0 plus beta 1 x 1 I beta 2 x twice I, and it will go up until beta p x IP. So I write here, so let me write here I1 and I2 and then IP, and then this is what I can write in here, sum of beta j x ij. Okay, and then it is going, j goes 1 to p, j goes 1 to p. So I write log lambda, which is the average number of accident or average number of phone call drop or average number of like average number of patients have a specific kind of diseases. Okay, I can write log of lambda like this format. Okay, log of lambda I can write like this format. So I can write here lambda equal to what? Lambda equal to e to the power sum beta j x ij. So it is, I can write here j goes 1 to p. So these things I can put there, right? Log of lambda is a linear combination of the covariate. If I want to predict the number of accidents, average number of accidents, this is the age of the persons who are involved in the accidents. This is the educations of the persons who are involved in the accidents. Okay, this could be the locations, and this could be the income level. This can be the gender. All of these covariate are used in order to predict the average number of accidents. Are you okay with these things? Clear, right? Okay. Now, I want to say that y is the response variable. This is the average. which follow the Poisson distribution with parameter lambda. Now, likelihood function of the Poisson distributions. Now, likelihood function of the Poisson distribution could be written L over beta. I'm going to ultimately everything will be in the format of a beta, so that is why I put here L over beta, and this is the multiplication. I goes 1 to this e to the power minus lambda, lambda to the power y divided by factorial y. Come in there. If I take the log of beta, taking log on both sides, we get L beta equal to y log of lambda and then minus lambda minus log of y. So now y would be this. I can put here yi, and log of lambda would be replaced by beta j x I j. Here I goes j to p minus e to the power beta x I j. J goes 1 to p or 0 to p. J goes 0 to p as mentioned in there. Here is 0 to p because this is 0. So I want to consider here 0. So if I put here 0, then this will be equal to 1. So for example, xi0 means 1. Okay. Take a pause in there. Are you seeing likelihood function? How did I model lambda by the beta z? Now lambda gone. Are you seeing the top function? I write likelihood function L of beta because these beta are a linear combinations of the predictor which I need to estimate. So derivation of the Poisson regression is nothing but the estimates of the betas, right? Estimates of the betas. And then it is log of yi. So now if I plug here the value of the z, like 1, 2, 3, 1, 2, 3, this is right. So now with respect to beta m, a specific. So if it is now differentiated with respect to beta n, if it is differentiated, then take a look what I am getting in there. Sum of x, I, m. So here, if I plug j equal to 1, 2, 3 up to m, if I plug here m, then this will be Im, right? That will be Im. And then what I have, yi. Okay. Similarly, if I differentiate these things, I got e to the power beta x, I, j. That is what I got. Anyone has any question? That one? This is the log for the denominator. So that is what equal to this. Understand now? Yeah. Now you got it, right? And then if we differentiate this thing, this is equal to 0. Do you have a question? Are you understanding this differentiation? Yes. So from here. So this is the likelihood function for the response variable y. Y is my response variable, number of accidents is taking place, right? But lambda equal to what? Lambda is the average, right? And regression means we are doing average things, right? So that means then if we take the logarithm of this, it look like that way. Now log of lambda, right? Log of lambda, I plug these things, right? Log of lambda. Don't you remember what I did in here? Log of lambda equal to this. Lambda means what? Average, right? Log of average. I'm modeling log of average as the linear combinations of the unknown parameter and covariate. Clear? You got it, right?
Convert it here, the last line is Im. How it's Im?
Okay. So now suppose if you plug the value in there, then what are you getting? If you plug 0, then you will get these things equal to beta 0 x I0 plus beta 1 x I1, then beta 2 x I2, and then you will got beta m x Im, right? And then you will continue finish beta p x IP. Clear? So in this case, now you are differentiating with respect to only that term, right? Because beta m, right? So that means this is all 0, right? You are differentiating with respect to beta m, right? You are targeting first, you differentiating beta m. First, you will differentiate beta 0, and then beta 1, then beta 3, then beta 4, then beta 5, then beta m. Each and every one you are pursuing. Okay, so this is the differential equations with respect to beta m. So now if you plug m equal to 0, it is 0, it is 0. M equal to 0 is in there. So in that case, you will get a 1 equation. If you plug m equal to 1, then it is a x I1, then this is a x. You understand, right? This is just only one quantity. And then if you plug x equal to I2 like this. So there are a lot of this type of normal equations you are getting. Are you okay, online people? Charity, are you okay?
Yes.
All Olado, are you okay?
Yes.
Good. Okay. So see, now if you plug m equal to 0, 1, 2, 3 up to all the way p, then you will get p of this type of equations. Are you understanding? Because you have to solve each of the parameter, right? Each of the parameter you have to solve, right? Hey, multiple linear regression model, when you write y, I, j equal to beta 0, then beta 1, x, 1i, beta 2, x, 2i, and then you will go beta k, x, ki plus epsilon I. Don't you differentiate with respect to each of these? It's called partial derivative, right? Partial derivative in order to solve each of them individually, partially differentiating. That is why this coefficient also called the partial regression coefficient. You can explain them partially. You can explain beta 0 keeping other fixed, other constant. Remember that, right? Nobody can explain, well, one unit change in x1, another one unit change in x2, another unit change in x3, and then joint change. There is no explanation like that. You can partially explain them. Okay, so now this is the one. Now, as I have how many equations in there? There are p plus 1 parameter, p plus 1 equations is in there. So it is p plus 1 equation. So in such a cases, we have to use, it is called the Hessian matrix. Hessian matrix we have to use, and then finally we have to use some computer algorithm to solve this. There is no closed form solutions. If I plug here, this is equal to 0, and then try to solve this, it will not be able, we would not be able to individually solve for betas. Okay. So here is some j's. We cannot solve it in this format. So this is called the suppose equation 1. Now equation 1 will be solved numerically using the Newton-Raphson method. Now Fisher information matrix is, and this beta can be obtained by, expectation has been taken like this. What does this mean? This is second order derivative, okay? So this is a second order derivative from the second order derivative of L. Is this from second order derivative of L. That means log likelihood functions. If it is taken like this, beta M, beta L, then this quantity come into that. Okay, so let me control Z. Oh. Okay, so if I take the second order derivative of this, now the time it will be closed. I should not do that. I should not do that. Now let me see. It will be now closed. Is there any way I can open another one? The class is recorded now. That's the problem. I wanted to. I don't know what happened. It's multiple time happened these things. No. I cannot close it even. Okay. Now it's coming there. Can you see my board now? Online people, can you see my board?
Yes.
Okay. So now see what happened. Okay, what happened? I'm going to restart the computer for some reason. I don't know. It's happened multiple times previously also. Any other way I can write this? Any other, let me see, PowerPoint slide, okay. Okay, PowerPoint slide, let me see if I can write PowerPoint slide. Hopefully I can write in there. Yes. Okay, new idea comes. Okay, what I had after differentiating these things dl over d beta m, we got this equation xim yi minus e to the power sum of beta j x ij, j takes value 0 to p. Okay, now if I take a second derivative of this del L, del beta m and del beta L, if I take this derivative again, then we will end up with these things x I m xil e to the power p beta j xij, j goes 0 to like this. So take a look at that. If you again differentiate this part with respect to now beta L, so you already have this xim in here. So if I multiply these things xim yi, and then I have xim, and then e to the power sum of beta j xij and p. Here is j goes 0 to like this. Now, if we differentiate this with respect to betas, then we will end up with these things. We'll end up with these things. This becomes 0, we'll end up with these things. So now these two equations these and that, these two equations will be used in that matrix. In that matrix, which is known as the I, Y, beta, expected value of beta, and this. In this matrix, we will have all of this. So now, in here, if we write our xj equal to x1j and up to x and j, which is called the jth column of matrix X, which is a covariate matrix. Okay, and defining the diagonal matrix, and we want to define a diagonal matrix, and diagonal matrix, we want to define a diagonal matrix which is W equal to WB it will go all the way beta j x and j. So this is the diagonal matrix we can define, and from there in a matrix format, finally these things come into that place: beta m, beta l, m, t, w, x, l. So we can write this quantity minus x, w, t, and x. Now see, lot of covariates there. How to write all of these things in a smaller format? That is why simple linear regression model to everything. Remember, simple linear regression model was this format: y equal to beta 0 plus beta 1 x1 plus epsilon. But multiple one was written x beta plus epsilon. X is a very big covariate matrix, and this is a betas, right? This is X, this is betas. Similarly, in this case, everything is shortened to this small format, and from there is a solutions of after this, after differentiation, they apply Newton-Raphson method to end up with the solutions for the A's, beta, J's. So this is the way all the beta J's are obtained, and then after obtaining beta J's, excuse me, the predictions are made for the response variable based on the covariates. Okay, this is the all solutions in here. There is no right. Okay, so let me tell you one thing. What is the difference between analytical solution, and numerical solution? Numerical solutions. You might wonder why there is not a explicit expressions of this one. I want to see a very explicit expressions of the beta J's from the Poisson distribution. These might be in your questions. There is no explicit expressions for that one, because after differentiating, take a look at that. After differentiating, I even cannot go there. After differentiating, first differentiation, we got this one. From there, if we equal to 0, we cannot get very beautiful closed format solution for the betas. Understand? Do you understand? This is the first derivative, right? From the first derivative, we are expecting what? The solution for the beta 1, beta 2, beta 3. But this is the equations, right? From these equations, there is not a closed form, very beautiful mathematical expression of the betas. Okay. When there is a very beautiful mathematical expectations that I discussed in the first class, do you remember? I derived these things, right? This is what I remember, right? This is a very closed form, right? And then I also derived these things. Beta 1 hat equal to sum of x, y, and sum of x bar. I think sum of yi, and then that is sum of x square and sum of x square over n, something like this. This is a closed form. This is a closed form solution. This is called the closed form mathematical solution. Mathematical solution. Okay. Or analytical solution. Analytical solution. Understand? Analytically, mathematically, you can derive these things very beautiful closed format. But in this case, after second derivative, you got some results that is not in the closed form solutions. After second derivative, you got this one. Okay. Then the Fishers give a matrix. This is called the matrix. This is equal to second derivative. This is equal to second derivative information criteria. From there, we have to use Newton-Raphson method. Let me see the Newton-Raphson method for that one. Very explicit Newton-Raphson method is in there. I have written somewhere. Let me give that. Just a second. So you might ask, where is the Newton-Raphson method one? Where is the Newton-Raphson method one? That must have somewhere come. Must be somewhere I have written. Okay. I think if we want to write this, So it is- let me find that for you. Cluster analysis, that is my logistic regression. This is classification. Is now the thing in the 1, 2, 3. One. Cox proportional one. I have a easiest one so that you can understand the Cox model. Yep, I got the Newton-Raphson method on. So let me write the Newton-Raphson method. Why I find all of these things, otherwise you might have a problem in understanding this. So Newton-Raphson method solution is this. Beta m hat could be obtained. This is the initial guess of the beta m-1, and then take a look at that. After that, you are going to use these things in here. Beta, double beta, L. So, and then you can put here beta hat m-1 and y comma x, y comma x. This is a, and then here I am putting beta L. And then here I am putting beta hat. Now I am going to explain these things to you as well. Y given x. Now remember, the Newton-Raphson method is telling you these things, right? X n equal to x n minus 1, and then this is a functional value, and that is a, right? For the linear quadratic or so not linear, for the quadratic cubic or any continuous functions, this is the solution, right? This is the solution, right? Newton-Raphson method that we derived. Now take a look at that. In this minus sign at that minus sign, right? This initial guess, that initial guess, right? For the Poisson regression model, and this is called the negative one. So which is coming to the denominator, right? Now take, this is the double derivative. This is just the single derivative. Understanding? So our function was what? Our function was no derivative divided by first derivative. Here is first derivative divided by second derivative. Because you are getting solution from this first derivative actually. After first derivative, then we get the solutions, right? So that means that equation. So this is the equation that we want to have the solution. This is the equation. Fx is the equation. So that is why this is the first derivative. From the first derivative, we are getting the solution. So what I wrote in there, this is what I write in there. This is first derivative, and that is second derivative. First derivative and second derivative has been put where? here. So this is the Newton-Raphson method in a linear, very simple format. This is in the matrix format. Okay, this is the first derivative. This is the second derivative. We want to have a solution from the first derivative, right? We want to have a solution from the first derivative. What? This one? This delta? Yeah. This is BB means double. This is the single one. So that means that is actually this is the double one, and I cannot go up now in here, but here I wrote it in here. This is the single one. This is equal to delta B. This is equal to delta BB. Okay. So this is in the numerator. This is in the denominator. Because from there I want to have this. Want to find the solutions. In order to have the solution, I need to have equation, right? So that is our equation, right? After derivating, that is our equation. Maximum likelihood means what? So after first derivative, you have to find the solutions, right? Maximum likelihood definitions is the. So that's the reason they put all of these things in this format. You are still struggling? Take a look again. This is the Newton-Raphson method that everyone in this class understand. I derived these things from a simple geometry. There is no questions, and a example, numerical example was also given, right? So I have to bring the solution in this format because after first derivative, no people on the planet of the earth can find the solution from this one. After first derivative, this is the one which if I put here, nobody can separate others from betas. If there is a way to separate these things and finding the betas, then we should not go to the other one. Why? This is the maximum likelihood function. So do the first derivative and find the solution, that will be your solutions. So this is not possible from here. So that is why we came here for the second derivative. Why we take the second derivative? Because this will go to the numerator in the Newton-Raphson method. This is the numerator of the Newton-Raphson method. This is these things. Let me take this color. This color is the first order derivative. This will go in there. This is the second order derivative, which is in there, which is true. Like you are seeing this, right? Inverse, right? So why there are second derivative? Why? But original function, there is a first derivative and no derivative. Original function, there is a first derivative in the denominator, and in the numerator, there is no derivative. So our equation is this one. Our equation after first derivative, this is our equation, which will give us maximum likelihood estimate according to the definition. So that is why you are seeing that there is a first derivative in here and the new denominator is the second derivative. But concept is coming from Newton-Raphson method. Understand, right? And sorry, because I messed it up. I really wanted to put this lecture in the online so that people can understand. But anyway, whatever I have done this. Next class, we will derive negative binomial distribution. And first of all, I will discuss what is negative binomial distributions, how these come into an existence, what are the situations, the derivations, and then I will go systematically for the derived. And next class, entire negative binomial distributions will be derived in one lecture, and then I will discuss some real life example. Code will be provided and homework will be uploaded. Okay, so up until now you are free for the 2 weeks, almost no homework. Okay, see you next week. Bye.
Bye.